Okay, everyone, welcome to section 11. This is Sakib. I'll be talking to you today about defensive expenditures. Now, I think defensive expenditure was actually included in your section notes from last week, but we didn't actually cover it in the section video. So the plan for this week is to go over defensive expenditures and do a few problems with it. So what's going on with defensive expenditures? So in this part of the course, our goal is to kind of value things that are hard to value, like pollution or air quality, things that don't necessarily have a market price, so we don't know exactly how to go about uh, valuing these amenities. So until now, we've been doing hedonics, where we try to look at market prices and carefully um, go through ideas of accounting for other differences and sorting to put a price tag on certain amenities. But in defensive expenditures, what we do is we look at people's expenditures on things like mitigating pollution or raising environmental quality, and we look at that expenditure and then we try to put or make some kind of a statement on how much people value pollution or environmental quality. So to take a simple example, let's think about the wildfires in California last year. Let's say in response to that wildfire, I buy an air purifier. And so what kind of a statement can I make based on the fact that due to this increased pollution, due to the wildfires, I bought an air purifier, and let's say the price of that air purifier was $500. The statement that I can make is that I value that increase in pollution by at least $500, okay? As in, to avoid that increase in pollution, I'd be willing to pay $500. So that's kind of like a lower bound on how much I value decreased pollution, okay? It tells me that's how much I at least value a lower level of pollution. Um, so if I want to be a little more rigorous in this, let's start with the math. And before I actually introduce the math on defensive expenditures, let's do a, let's do a little bit of a background on calculus. Now, let's say we have some function f that depends on some variable t and some other variable x. But let's say the variable x itself is dependent on t. Okay. Now, if you want to figure out how f changes when you change t a little bit, you have to take two things into account. You have to take into account what the direct effect of f is when you change t. Okay, so you change t, you directly change f, so you have to take that into account. That's just this. But you also have to take into account that when you change t, you change x, and that in turn changes f. So you have to take into account what the effect of changing x is on f, and that's due to x changing because of t. Okay, so again, because of changing t, over here you're changing x, that changes f, that's this part over here, and because when you change t, you directly change f, and that's that part over there. Okay, now armed with this, let's look at what's going on with defensive expenditures. So let's say we have some expenditure function d. So this is how much you're going to spend on environmental quality. That expenditure will depend on Q, where Q is environmental quality, and P. Okay, and P is pollution, the total amount of pollution in the air, let's say. Okay, so what are these alphabets? So D is your expenditure. Q is, let's say, environmental quality, which is quality, and P is pollution. Okay. Now, what we're interested in finding is how my expenditure changes when pollution goes up by a little bit, and that's the basic idea on putting or inferring willingness to pay for pollution. We see a change in pollution, people change their expenditure, and then we can make some kind of a statement on how much they value that change in pollution. Okay, so we want to know how D changes when P changes. Okay, so DP, when pollution changes, how does expenditure change? That will be partial D, partial Q. dq dp plus partial d partial p. Okay, and this is basically something that just follows from that. It's the exact same thing. Okay, now where is this object coming from? It's coming from the fact that environmental quality here is actually a function of P, okay? How much environmental quality you're going to choose to consume will depend on the level of pollution in the atmosphere. So Q itself is a function of P. So Q is a function of P. So when you're changing P, you're changing D in two ways. There is the direct effect of changing P on D. And when you change P, you change Q, and that in turn has an effect on D. Okay, so there's two components to your change in expenditure. There's a component that comes directly from P, and there's a component that comes because of P changing, which changes Q, and that in turn changes D. Okay. Now, what we're really interested in is this object over here, okay? The change in expenditure that comes solely from a change in pollution. But what we observe is actually this, okay? When consumers change their expenditure and we observe it in real life, what we look at it is this, which is the combined effect of a change in environmental quality and a change in pollution. But what we're really interested in is just solely the effect of pollution. Okay, so we don't actually see this. Instead, we end up seeing this. Okay, and the idea here is that dD dP is an underestimate of what we're truly interested in, which is partial D partial. Like that. Which is an underestimate of partial D partial P. And why is that? Because it turns out this object over here is less than 0. Okay, so basically this over here will drag this one down and we'll get an underestimate. And so why is that? That's because dq dp is less than 0. Why? The idea here is that when pollution goes up, environmental quality goes down, so this is less than 0. And turns out this is greater than 0, partial d partial q is greater than 0. Why? Because if you want higher environmental quality, you're going to have to spend more. Okay, so this is greater than 0. So that means this whole thing is less than 0. That means what you observe is less or an underestimate of what you really want to see. Okay. All right, so that's the math on defensive expenditures. Now let's move on to exercises. Okay, so now we're going to do exercise 1.1, the first question on defensive expenditure. Again, I'm going to assume that you're going to pause the video right now and read the question first before coming back and resuming the video again. So before we do the exercise, let's kind of look at the general structure of a defensive expenditure problem, or at least an algebraic defensive expenditure problem. Typically, you're going to have some kind of a utility function, and the utility function is going to be dependent on x and q, where x is some kind of a composite good, like a combination of all other goods you consume, and q is again environmental quality. So your utility will depend on the composite good x and environmental quality. And then you're always going to have some budget constraint y, and that's going to depend on how much you spend on x and how much you're going to spend on the environmental quality q. So how much do you actually spend on q? That's just your defensive expenditure, dqp. And how much you spend on x is just 1 times x. So the 1 is basically the price of x. We kind of assume that x is price of 1. So it's just x, okay? dqp plus x, that's your total expenditure on x and q. This is how much you spend on environmental quality. This is how much you spend on all other goods. Okay, and so the exercise that we're going to do is also going to follow that same structure. In fact, like most defensive expenditures problem kind of follows the same structure, and that's why I would say it's relatively easy to solve these because it's kind of mechanical, algorithmic. You follow the same steps over and over again. So what's going on in this exercise is you're given a utility function. So exercise 1.1, you're given a utility function that looks like xq. Okay, so this is the utility function, this one over here. Pretty simple utility function. And then you're given that your D, your expenditure and environmental quality, is PQ. That means your Y, again, coming from this, is going to look like this, PQ plus X, okay? And that's your budget constraint, remember, this is your total income, so that's your budget constraint, this is just your utility function. These problems are related very closely to consumer utility maximization that you've done in Econ 100 or EEP100, so basically microeconomics. Okay, so we're going to try to maximize consumer utility with respect to Q. So what's the first thing you do? So, okay, the question asks, okay, what are optimal X and Q and given a certain budget constraint and pollution level? So you have to figure out what optimal X and Q is. You have to maximize utility with respect to X and Q. Again, this kind of should remind you of consumer utility maximization. So the first thing you want to do, okay, so our idea here is that we want to maximize X and Q given utility equals to XQ. Now, we actually don't have to take Lagrangians in this case, like you do in consumer utility maximization. What you do, and again, this is something you're going to do for all defensive expenditure problem, I would say this is step one. The first thing you do is you substitute X from budget constraint. So what do I mean by that? You know that Y equals to PQ plus X. That means X is equals to Y minus PQ. And you're going to take that and you're going to plug that in to the utility function, okay? Step two, plug X into U and maximize, and then solve for Q. Okay. So what are we going to do? We're going to take this X we found and we're going to plug it into Q, and we get this, and then we're going to take the derivative of this with respect to Q. So we're going to do partial U, partial Q. So we're going to get Y minus 2PQ equals to 0, and then we're going to solve for Q. If we do solve for Q, we'll get Q equals to Y over 2P. And then in the question, you're told that Y is 10 and P is 1. So Q in this question, the Q that's going to maximize consumer utility is just going to be 10 divided by 2, which is 5. And given this is the Q the consumer is going to choose, the X the consumer is going to choose is going to be based off of this, right? Now you know what P is, Q is, and Y is. So X is going to be Y minus PQ, which is just 10 minus 1 times 5. Okay, that's 1 times 5, and that's just 5. Okay. So that was part A. Okay. And now part B tells you, okay, now we know how to solve for Q, and we also know how to solve for X. So in part B, it gives you different values of P and Y and asks you to figure out, okay, what are optimal Q and X? So part B, Roman 1, now you're told that P is 2, Y is 10. So what's Q going to be? Q is again going to be Y over 2P, 10 times 2 times 2, so that's just 2.5. And given that's P, X is going to be again Y minus PQ, and Y is 10. Now P is 2 and Q is 2.5. That's just going to be 5. Okay. And Roman 2, pollution stays the same, P equals to 1, but now Y increases to 20. So we do the same thing again, re-optimize to find the optimal level of Q and P. So now you have Q equals to Y divided by 2P. Now Y is 20, P is 1, so you get Q is 10. X is going to be Y minus PQ, Y is 20, P is 1, Q is 10. So the optimal level of X is 10. Okay. Okay, Romans alphabet C. Now you're asked to figure out what the change in D is when P goes up from 1 to 2. But Y stays the same, okay? Y stays at 10, your income stays the same. And in terms of algebra, straightforward, we know that when P equals to 1, the environmental quality is 5, and when P equals to 2, the environmental quality that the consumer chooses is 2.5. If you're confused where I'm getting these, it's just what we did in, so for example, in question A, we figured out that Q is 5 when P is 1. And then over here, we figured out that when P is 2, Q is 2.5, okay? So that's exactly what I just wrote here. And now we're asked to find what the change in D is. So D, in this scenario, remember D is just, D is simply PQ. So in this scenario, it's 1 times 5, so that's just 5. In this scenario, D is, again, PQ, that's 2 times 2.5, again, that's 5. So the change in D is 0. Okay. Now, the algebra or the math, at least for this question, is pretty straightforward. But the intuition, I think, is what's more important for this math. So essentially what this is saying here is that even though the level of pollution went up from 1 to 2, there was no change in defensive expenditure. And so if you inferred the value of an increase in pollution based on this calculation, you would say that consumers simply don't care about an increase in pollution at all, since the change in defensive expenditure was 0. But as we know from our math earlier, from over here, that's not the case, because what you observe is an underestimate of how much people actually truly value pollution. And so the idea here is that when the level of pollution goes up from 1 to 2, people are optimally choosing to actually consume lower environmental quality. So the level of Q goes down from 5 to 2.5. Okay. And so again, the idea here is that this holds. Okay. So it's dd by dp that's actually 0, not per shell d per shell p. Okay. And there's a very closely related problem also in your problem set, in problem set 7. Okay, so let's move on to number 2 now. Okay, so the idea for this question is Jim's living on a hillside. So his house is located somewhere on a hill somewhere. There's a slope, okay? And so there is a mudslide risk. And so Jim decides to build a wall to protect himself against this mudslide risk, okay? There is some kind of a wall. Again, excuse my terrible drawing. And the idea is now climate change, because of climate change, Jim has to build a bigger wall. Okay, so he has to increase the size of his wall, and due to this increase, he has to spend an additional $10,000. Okay. Now, but there is one more thing that you need to know about this question. It's that the wall doesn't just provide protection against mudslide, but the wall also provides other utilities like shade and a drawing area for his kids. So there's other uses that Jim gets out of this wall. Okay. And so then the question is, since there is an increase in climate change, now there is an added risk of mudslide, so Jim decides to spend an additional $10,000 on the wall. Does this imply that Jim values climate change exactly at $10,000? Or like, what can you comment on that statement, okay? Does that mean the willingness to pay for climate change is $10,000? And so to answer this question, so basically it's a verbatim, this is what the question says. In that case, what can you infer about Jim's willingness to pay to prevent climate change from his expenditures on the wall? So there's two things that you need to keep in mind.
the first thing is what we've been talking about so far, that defensive expenditures are going to be an underestimate of the true willingness to pay. Okay, so DD DP, what you observe, which in this case is this $10,000, is going to be an underestimate of partial D partial P. Why is that? So just to make things a little more concrete, D in this case is again expenditure. P is, in this case, what goes up? Climate change. So P is climate change, and Q is environmental quality. So Q going up is a good thing. So you want to say Q is protection from mudslide risk. Okay. And so again, what we're saying here is that this, whenever climate change goes up, the expenditure that you observe, which is this $10,000, is going to be an underestimate of the true willingness to pay to avoid climate change. And the basic idea here is that now that climate change has gone up, Jim just accepts a higher level of mudslide risk. Okay, and so Jim just accepts a lower Q in this case. Okay, so that's one thing that you'll have to mention. So in that sense, it's an underestimate. But then you'd also have to take into account the fact that the wall has other uses. Now, what that means is like the 10,000 that Jim's actually spending on the wall isn't just protection, but it's also for things like shade and drawing, which means this 10,000, like from that 10,000, some of that money is at least for these other uses. So in that sense, this 10,000 is an overestimate of Jim's true willingness to pay to mitigate climate change. Okay, so then we have these two forces working against each other. There's the underestimate because Jim just accepts a higher level of risk over here. And then it's an overestimate because the wall has these other uses like shade and drawing. So you don't know which exactly dominates, if this dominates more than that or this dominates more than this. And so you don't really know then from all of this if 10,000, the 10,000 amount is an underestimate, an overestimate, or an accurate estimate of the true willingness to pay to avoid climate change. Okay. All right. So let's just end here.